what they thought might be really interesting, an old lake bed. The old lake bed, however, was covered with this basaltic material that had covered the really interesting stuff, which might have been a fair bit deeper. And so they really didn't get to evidence of aqueous transformation until they trudged over to the hills, and that's where they are now. Actually, that rover is still working, but one of its wheels is gone, and it's kind of been stuck in one place for quite a while. But both of these landers were just tremendously successful. Here's Opportunity again from space. If you look real carefully, you can see it. The arrows are pointing to it and also pointing to its track over by Victoria crater. And just some spectacular images of that. Being all Mars Society people, of course, you should have your stereo glasses on, and you'd be able to see this in stereo. But this panoramic, if you look at it on the web in stereo, is just incredibly spectacular. And of course, Opportunity went down into various craters and is now trudging off trying to find another one. So I won't talk about Phoenix. Brett talked about that. But just a little bit about how Mars is different from Earth. Earth, of course, is covered with both continents and water. Mars has no liquid water that we can see to any extent on the surface. The moon actually stabilizes the obliquity of the Earth, and so it doesn't vary around in time. But on Mars, that varies around in time, and that leads to some interesting geology. For example, the polar ice caps moving around on these kind of 100,000 and longer time periods. And of course, the atmosphere of Mars is much less dense than Earth, about 1/100th, and primarily carbon dioxide. And so the question of the day really is, is there microbial life there now? But probably more importantly, can we get down to the surface and look for what might have happened in the past, and compare a little bit about what we think we know about the history of early Earth and what we think about the history of early Mars. In early Earth, billions of years ago, more than 3.8 billion years ago, there was all this stuff flying around the solar system. The Earth was bombarded with lots of impactors. A lot of the evidence of exactly what that was like has been destroyed because the Earth has plate tectonics, and the continents eventually get buried and subducted and get hot and then come back up and then come back up. And so you don't really have a lot of chemical evidence left of these very, very early times. That probably froze out very early on Mars. So potentially on Mars, we might be able to get back to a very early time with chemical evidence and see what's there. The Earth, of course, had oceans early on. It was an iron-rich ocean early on, but there wasn't really much oxygen at all in the atmosphere. And then the atmosphere gradually, as time moved along, got more oxygen-rich. We believe microbial life developed very early on, even without oxygen. And then more complex life, multicellular life, probably didn't emerge till much more recently. On Mars, it was kind of a bit of a different history. Early on, it was almost certainly very much more water-rich. How long the water stayed around, for hundreds of thousands of years or for millions of years is a question that's being asked, but there's certainly evidence of water flow. Early on, there were clays chemically formed by surface water, and we can see spectroscopic evidence of those from space right now. And that's probably plausibly the time, that Mars was most habitable on the surface. Then there was a period where kind of the surface chemistries got influenced by volcanoes. You see these really huge volcanoes on Mars, Olympus Mons and so on. And that certainly is the chemistry, and there almost certainly was some sort of fundamental climate change that happened in that time. And because of all the volcanic activity, a lot of the chemistry kind of got dominated by sulfur chemistry. So now the surface tends to be more acidic and more sulfur chemistry dominated. And in recent billions of years, the geological activity of Mars has probably really slowed down. We don't really know if there's anything much coming from the interior of Mars or not, although we're seeing some really interesting results that I'll talk about in a minute of a very simple hydrocarbon, methane, which is showing up in the atmosphere of Mars. So Mars, which early on may have had kind of a molten core in the middle, had a magnetic field due to that magnetic core. That probably froze out because Mars is a small planet much earlier than on Earth, and the interior of Mars now may be cold, and that kind of influences what happens at the surface because you don't have things moving around and as geologically active as they are on Earth. So how do you get at this life question? Well, life produces complex molecules as well as simple molecules. And in the simple molecules, some of them can go into the atmosphere and you can measure them. So one way to start the search for life on Mars is through remote sensing of things that might be produced from biology, such as methane. In the Arctic, there are all sorts of methanogens, methane-producing bacteria living in the permafrost, although a good share of the methane comes from cows and actually other types of mammals. And so one way to start the search for potential biomarkers is to look for some of these trace gases. That's very, very difficult to do from Earth, and would be easier from orbit, but of course it's much more expensive to do from orbit. That search has really started. Geronimo Villanova is shown here down on the bottom right, and his analysis of data from a program that Mike Muma at Goddard started showed these color-coded on the left signatures of methane way down in the parts per billion, very, very low traces of methane. But the really interesting thing about that detection is in the atmosphere of Mars, photochemistry, all of our models suggest that methane, if it was produced, it should last for quite a few years, maybe 350 years. By golly, when Mike Muma and Geronimo looked for methane, they found it, but then a few months later it appeared to be totally gone. It's a very, very difficult set of data taken from a mountain in Hawaii, a Keck telescope that gets above much of the atmosphere. And so if methane is being destroyed, how is it destroyed is still an outstanding question. And where it comes from is also is not known. Of course, it would be really interesting if it was from biology, little pockets of water way down deep, happily producing methane, as is kind of shown in this animation on the left. Or it could be from inorganic reactions, very deep water in the subsurface, and then some vents that are leading up to the surface. And the artist at Goddard tried to kind of illustrate that as well. And, you know, potentially at certain seasons, as the ices on the sides of these hills melt, then the methane has a path to escape. And so it's really a fundamental question where methane is coming from. Is it one of the signatures of life that's on Mars or not? Of course, life produces, in addition to simple molecules, produces these complex molecules. They're not going to go into the atmosphere in this very cold environment. And so the only way to get to them is to go down in the surface and dig around and get into old rocks. And that's what we're intending to do with the Curiosity rover. For those of you who've taken organic chemistry, these little stick-type figures are just carbon atoms, and showing the structure of the carbon atoms as I've illustrated below. And it turns out that life tends to put patterns into, it creates order out of disorder. If you make organics in space and you look at carbon that comes in from meteorites, it's kind of randomized. It's radiation chemistry that randomizes organic molecules. But if you look at things that life produce, you have little enzymes, for example, chomping off or producing two sets of carbon atoms at a time, and so you have structure in your organics. And so the hope with the MSL instrument is that we might find some of those organics and at least look for those patterns. For example, if you have a crocodile or alligator, whatever this is, and it has a happy life and then turns into a skeleton. Similarly, if you have a membrane of a cell and the cell is dead and gets buried in a rock somewhere, if it's a robust enough molecule, that molecule might be changed a little bit, as is shown here, but it's still there unless there's some process that's really vigorously destroying that. And so just like you would have a skeletal fossil on Earth, you might have a molecular fossil that'll tell you something about Mars. And like I mentioned, there are patterns in these molecular fossils, and the patterns tend to be things that are 2 carbons apart. And so